Hello class, this is lecture 24 for Econ 8711 and I'm your professor John Raybeck. Great, so this lecture is going to cover going from demand to preferences, and we're going to introduce Roy's theorem and the Slutsky equation, and this will be the last lecture of this class. Great, so here we're going to make several assumptions for these results just to make things a little bit easier. And the things that we're going to assume are going to be strict convexity, continuity, and local non-satiation. Right, so the reason we're going to assume strict convexity is so that we know demand functions are unique. And in this case, we'll talk about a lowercase d, p comma m for Marshallian demand at prices p and income m, and h p comma v for Higgsian demand. So again, v is the level of utility and p are prices for this Higgsian demand. So how do we obtain Roy's identity? Well, recall that we can look at the derivative of the expenditure function with respect to price n in order to get Higgsian demand at utility level v. Finally, we can suppose that v is equal to the indirect utility, right, for the expenditure function at utility level v, right? So we use this from the past lecture. For this equation, we can differentiate with respect to Pn then, in which case, we'll have to essentially like a chain rule going on here. So we get the derivative of the indirect utility with respect to price Pn plus the derivative of indirect utility with respect to the income component times the derivative of the expenditure function with respect to price of n. So from here, we can rearrange to get h of n. So the Higgsian demand of p comma v is equal to the ratio of partial derivatives of the indirect utility with respect to prices and the indirect utility with respect to income. But by making the appropriate substitutions by letting, say, v be the indirect utility instead at expenditure m, then we'll get that this is in fact equal to the Marshallian demand at prices p and income m, right? So here's Roy's identity. So it gives a relation of the demand to the ratios of indirect utilities. So this has its own slide. So why are we, giving this so much thought and space? Well, Roy's identity is going to allow us to say things about preferences from demand, right? So this tells us something about, the ratio of indirect utility with respect to the ratio of, just ratio of changes of indirect utility and relates them to demand. But this will allow us to say things about preferences. So for example, if m is fixed, then we could integrate along values of p to obtain estimates of, difference in utility for an individual, right? So we'll be able to just integrate along this path, and then this will be able to tell us something about changes in welfare. But integrating along this path now, we just need to observe demand in order to try and find the changes of welfare. So this allows us to integrate over an observable thing in order to try and say something about unobservable indirect utility. And again, this allows us to recover this information about welfare from just demand functions. And again, this is useful since it is hard to know what an individual actually prefers. And in economics, we regularly assume that the only way we can tell something about preferences is by looking at the revealed preferences. So we use the choices an individual makes in order to say something about the preference relation. Great. So that's the end of Roy's identity. The next thing we're going to talk about deriving is the Slutsky equation. And here we're going to consider the identity that Marshallian demand evaluated at income from the expenditure function at utility level v is equal to the Higgsian demand function. So we can differentiate this identity with respect to some price pj, and then again we can, we need to differentiate this with respect to each thing. So essentially there's a chain rule going on here. So we get the derivative of Marshallian demand with respect to the price of j, the derivative of the Marshallian demand with respect to income m, times the derivative of the expenditure function with respect to price j, and this equals the Hicksian demand function differentiated with respect to prices pj. Right, so from here then, we can make the appropriate substitutions, and if we do this, then we'll get the following. So we'll get that the change in Marshallian demand with respect to price pj is equal to the change in the Hicksian demand with respect to price pj minus the demand of good j times the change in demand of good n times the income, or times the change in income of m. Right, so this is just by making the appropriate substitutions. But why is the Slutsky equation useful? Well, first, this allows us to document lots of comparative statics, right? So we can start to relate things like normal goods, inferior goods, complements, and substitutes, all by using the Slutsky equation. This is also a nice application of duality, right? So we're able to relate all of these comparative statics by writing down these two problems and looking at the relationship between them. Finally, this also gives shape restrictions. So remember, the Hessian of expenditure function is convex, and this means that the derivatives are positive semi-definite. So in fact, since the derivatives of the Hicksian demand function are positive semi-definite, this will place additional restrictions on the Marshallian demand functions and how they change with prices and income. Yeah, so how do we interpret parts of the Slutsky equation? There's going to be several parts. So essentially there's a compensated price effect and there's an income effect. And I'll go back to the slide on the Slutsky equation to show how these show up shortly. And these two effects can be broken up graphically for two goods, but the Slutsky equation we have here is an algebraic generalization of the thing you may have seen in your intermediate microeconomics class. So what do I mean by there's a compensated effect and a income effect? Well, here, this is change of demand holding level of utility fixed. Right, so this is how you would change your demand if you were minimizing expenditure and just a price was changing. So this is related to just a price change of the Marshallian demand. And this second part is an income effect. And the reason this is an income effect is that as the price PJ changes, really we have a function of income that depends on prices, right? So, recall for locally non-satiated utility functions, we have that M is equal to P inner product X. But if we differentiate this, then our income is really changing at rate just X of J, right? So our income changes at this rate, and this is what's captured here. And the reason we have a negative sign is because, whenever we're taking derivatives with respect to a price, we're always thinking of this price increase. So our income is really decreasing at rate dj, and then our demand for good n changes like it does scaled now, changes like it does with income, but scaled by the size of dj. Right, so that's how the two effects show up in the Slutsky equation. Great. This is the last lecture. We discussed these two final properties of demand and discussed why they are useful. We did not discuss sufficient conditions for these to hold other than assuming high-level conditions on the indirect utility function, right? So we assumed these were, strictly convex and, differentiable enough in order to look at these things. But other than that, we didn't talk about the conditions under which this will hold. But strict convexity and differentiable utilities are fairly common in applications. So these types of results are useful and they do show up fairly regularly. Anyway, thanks for listening.